premise of this presentation is that forces are not just a push or a pull, or ghosts that act at a distance the way gravity or magnets work, but they are energy transfer between objects. As usual, this preview allows you to skip parts you may be familiar with. Starting at slide 3, I present the standard interpretation of forces, both contact and at distance forces. Slide 8, I redefine motion and energy. At slide 12, I redefine forces. And at slide 18, I let artificial intelligence have its say on the topic. Every physics book defines a force as a push or a pull that, if it's unbalanced, it accelerates an object, or, depending on the angle at which it's applied, it can also change the direction of moving objects. This being a practical definition. Since gravity and magnetism can also be accelerating objects without actually contact, we say that forces are either contact forces, forces that objects touch each other, or at distance forces, forces that act through a field, whatever that field may be. Newton codified the concept of forces into 3 laws. The first one says that an object at rest will remain at rest, while an object in motion tends to stay in motion unless a force acts upon it. This is called inertia. But why masses resist acceleration is left unexplained. It's treated as a given. Second one says that forces do not just move masses, they accelerate them. And the formula is F equals ma. The third one says that to every action there's an equal and opposite reaction. In other words, forces always come in pair, or you can't have one single force. You can't push nothing. Newton's laws were practical, since he needed to contradict Aristotle's belief that the natural state of object was to be at rest unless forces move them. In other words, everything always stops. Of course, the concept of friction was unknown to Aristotle. As for gravity, Newton called it an at-distance force, saying only that 2 objects attract each other instantly depending on the masses and distance between them. No explanation was provided. And Newton knew about electric and magnetic fields, but he didn't comment about them as forces. Today we accept 4 at-distance forces. There may be a 5th force. These are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. All of them accelerate or change the direction of specific types of matter. Therefore, they are considered forces. For example, electromagnetism accelerates charged particles toward or away from each other, while gravity accelerates everything toward each other. Quantum mechanics assigns the transmission of at-distance forces to the exchange of particles called bosons. Accordingly, the gravity may be carried by a particle called a graviton with little mass. The electromagnetic force is carried by virtual photons, not the real photons, light photons, with 0 mass. The weak nuclear force is carried by the W and Z boson with some mass, and the strong force is carried by gluons with no mass. This concept is mathematically consistent, but we must remember that epicycles and Ptolemaic astronomy could accurately predict lunar and solar eclipses, but that didn't make the Earth-centered concept correct. To begin with, let's redefine motion as a relative property of space. By relative, I mean there is no preferred frame of reference, and that's one of the requirements of special relativity. By saying it's a property of space, what I mean is that objects can't move independently. A force can accelerate an object, but once that force is depleted, the object will stop moving. In our universe, what keeps an object moving with a constant velocity after the force is applied is universal expansion. In other words, masses can be accelerated, but the continued final velocity results from universal expansion. If the universe was to stop expanding, everything would stand still. Indeed, time itself would end. So, if motion is relative, then energy must also be relative since energy is 1 half mv squared. So, let's look at two balls, a dark and a gray one, and an observer that's stationary relative to the two balls, meaning they're not moving relative to each other or the observer. No energy is present in this frame of reference. In the distance, there's a white ball and an observer that's stationary relative to the white ball, meaning ball and observer are now moving relative to each other. There's no energy between ball and observer. If the balls and observers are moving toward each other, which grouping and which frame of reference has the energy? Obviously, we can't tell, and that's why I state that the energy is not with the object. The balls have energy because they're moving with universal expansion at different rates, these rates being set by whatever force accelerated them. Let me clarify something. Universal expansion cannot move matter, but it keeps matter moving at whatever speed and direction of force propelled it at. That's why I'm saying that energy is a function of or depends on universal expansion. Again, without universal expansion, time itself will not exist. In this example, when the balls collide in a perfectly elastic collision, the force of impact between the white ball and the gray ball ejected the gray ball and paired the white ball with the black one, the new pair continuing the black ball's trajectory. Two balls replaced each other. The question that arises is which ball, the white or the gray one, transferred its energy to the other ball? To begin with, none of the balls had energy relative to their observer. Again, that's why I believe that energy is not a property of masses, but arises out of universal expansion. In the grouping on the left, maybe the two balls were moving downwards and collided with a stationary white ball. That would assign the energy to the black and gray balls. In the grouping on the right, maybe the white ball was moving upwards and collided with the stationary gray ball. That would assign the energy to the white ball. Or maybe both the white ball and the black and gray balls were moving in opposite directions. Either way, to the black ball makes no difference. The observer with the black ball continues in its trajectory while the observer that was originally paired to the white ball is now moving with the gray ball. In these scenarios, we can see that the force is an instantaneous transfer of energy between two objects. Of course, we're assuming a totally elastic collision. There's no deformation of the colliding objects. That's the foundation of my belief that forces accelerate objects, but afterwards, objects move alongside universal expansion and energy is in space, not the moving objects. Without a force, objects can't move on their own, and afterwards, they must be carried alongside a propelling entity. Again, universal expansion cannot move matter, although it is involved in jiggling subatomic particles. As an example, electrons vibrating in the sun create light, which travels from the sun to the earth as a wave or photons. In space, it makes no difference what light is. When that light strikes a solar sail or solar cell, it pushes the sail or electrons, making them move. Now, according to Newton's third law, The light that pushed the cell or electrons must have a force component. But to scientists, light is a photon's momentum, but no force is involved. Still, Newton's law requires a force. It requires photons to have a force. And when the vibrating electrons in the sun produced that light wave, photon, or force, it must have pushed on something to transmit that force. So, just like in Newton's cradle, there must be something between the sun and the earth for the force to propagate. But that's a different topic. Let's look at distance forces, beginning with gravity. To Newton, gravity was intrinsic to mass. Masses instantly attract each other, and that force is proportional to the masses and distance between them. Einstein's genius was in moving gravity away from mass to space, making gravity a property of space. To Einstein, mass bends space-time, therefore objects follow a curved path around masses. To him, gravity was not a force, but a property of space anchored to masses. The other classical force we usually experience is electromagnetism. Hermann Weyl, a contemporary of Einstein, attempted to connect electromagnetism to space, but wasn't successful. Recently, building on the work of John Wheeler, a new theory is trying to integrate electric and magnetic fields into the structure of space-time, moving these fields away from charges and describing them as property of space. If this concept is eventually proven, electromagnetism will no longer be a force, but another property of space anchored to charges. We know that neither gravity nor the electromagnetic fields act instantaneously between masses or charges. They interact through their fields. Therefore, when masses and charges move, their energy extends to their fields. But energy depends on mass, and in the case of electromagnetic radiation or light, fields don't have rest mass, they have momentum. That momentum has equivalent mass given by the formula P is equal to m times c. Momentum is equal to mass times the speed of light. So each light wave has an equivalent mass that can exist only when the field is moving at the speed of light. That mass depends on the strength of the electric and magnetic field. So already we're seeing energy and mass as being defined as property of space in the guise of fields. As for the other at-distance forces, the nuclear forces, quantum mechanics assign their transmission to the exchange of bosons. If or when all forces are explained as property of space, just like gravity, nuclear forces will be merely anchored to protons and neutrons. All forces will be described as the geometry of space. At this point, I wanted to see how artificial intelligence would explain forces if I set up 4 limiting factors. Number 1, space is not emptiness. It has structure, it has density, it has dynamic behavior. Second, what we call mass is not stuff, but a region of compressed space. Third, what we call matter is mass bound with energy. Energy is needed to stabilize the compression through oscillation or geometry. And finally, space expansion, due to universal expansion, is a normal state of space, unless compression inhibits it. Forces emerge when we act to deform these balances. My interaction with AI was more extensive than what I'm showing here, and is a bit more technical, but I distilled it to the following slides. Forces aren't mysterious pushes or abstract fields. They're the physical process of transferring energy through space to reshape local density. For example, electromagnetic fields don't push particles. They reshape the space compression around them. In this view, every force becomes a field-mediated act of expansion modulation. Imagine trying to move an object, which I defined as a knot of compressed space plus energy. You're not shifting a ball, you're trying to rearrange space itself. That takes energy. The resistance to this shift is what we classically called inertia. The denser the knot, the more compressed the space, the more energy is needed to alter its motion. This reinterprets mass-based inertia as spatial rigidity, not an innate property of matter. Now let's reframe electric and magnetic fields. The electric field is a space tension gradient. It describes how energy wants to move through varying space compression. The magnetic field is a circulating energy pattern. It forms as expansion currents twist around moving space compression knots, like charges. These fields are not separate from space. They're simply how space expresses and responds to energy distribution and motion. This makes electromagnetism part of the intrinsic geometry of the expansion field. Now, picture a compressed knot, a particle, in a background of shifting density. If another charge or field distorts nearby space, energy flows through the gradient to rebalance the tension. The particle doesn't get pushed. Instead, energy flows through space into the knot, modifying its position or oscillation. This is a paradigm shift. There are no invisible forces. There's only energy moving through space architecture, rearranging how expansion is suppressed or released. Even light becomes a ripple of tension, a moving deformation in expansion density. So let's reinterpret the classical Maxwell equations in terms of space and energy flow. Where space is heavily compressed, a charge energy wants to flow outward. This creates tension. If tension shifts rapidly, it induces a twist. Space responds to dynamic deformation. There are no magnetic charges. Space can twist but not terminate. Circulations are smooth and self-contained. Currents and pulsing space tension causes magnetic rotation. These aren't abstract equations. They're field continuity rules for energy moving through a deformable medium. This framework naturally extends. Gravity emerges from radial expansion gradient. Denser regions inhibit outward space flow. Inertia is now seen as the energetic cause to reshape space compression. Electromagnetic forces become a high-frequency spatial modulation, and all of this eliminates the need for separate particles and forces. Everything is field structure and energy flow. What we gain is a unifying ontology. Space isn't a stage, it's the main character. Mass, energy, and motion are all expression of how space is shaped and how it unfolds. Forces don't act on objects. They are the tools by which space redistributes its own energy. This may offer a path toward reconciling gravity, quantum fields, and cosmology into a common geometric language. In summary, a force isn't something external. It's what a bit of space feels when it's sitting between more compressed space and less compressed space. Energy is the total effort stored in how space is compressed, stretched, or pulsing. It is an active state or stressed state of space. Momentum is a conserved pattern of moving spatial compression, a particle, within an unfolding cosmic field we call universal expansion.